Okay, so the way the attendance works is I take attendance at the end of class, and you're going to turn in these forms, and that's how I'm going to check to make sure that that you are here. Okay, I'll also do kind of a head count and just make sure that the number of forms I receive matches the head count that I get, just so people aren't turning in forms for other people and things like that. I'm only going to do it a few times during the quarter, maybe 4 or 5 times. Attendance was worth 5% of your grade total. If you leave early and you don't turn in your form, or if you leave early, you don't get attendance. Okay, there's because I have the quiz almost every week at the beginning, that kind of ensures that you are here for the quiz and on time for that. And so if you come later, if you miss the beginning of class, it's reflected in the quiz, and then if you skip out early, that's reflected in the actual attendance. Okay, and so that's why I do it this way. If you have misplaced this the little paper that I use for attendance, you can go on the class website, and there you can download a blank attendance form. You can download a blank one and fill it out with your number, okay? And if so I ask that you have one for the future, and I think you can get it right. Where is it? Okay, yeah. So a blank attendance sheet right here. You can just download it and bubble in your number. Well, if this loads. Okay, but anyway, it's right there, just on the homework page. Okay, are there any questions on how attendance works? Okay, so those of you who are, I guess, just watching the video, you can get the blank attendance sheet right here. Okay, anyone else? Any questions? Okay. And I do the attendance, yeah, just because, well, if you look around, it looks like some students skip out after the break, and so I just want to, I guess, kind of reward those who are stay through to the end. All right, and I like to think that the second half of class is just as valuable as the first half of class. So, okay, we will continue on here. We're still dealing with this data table, and we're going to select someone at random. Okay. And we asked earlier, I said, if I select someone at random, what is the probability that this person is liberal and a Democrat? And you guys answered, the fraction that I would write would be, what fraction would I write? 306 divided by 1858. Okay, that's okay with everyone, right? Okay, these are the people who qualify as both liberal and affiliated with the Democratic Party. Now, we have something called conditional probabilities. And we can ask something like, what is the probability that someone is a Democrat? And I put this vertical bar, which is read as given, liberal. Okay, so this is, and what this means is, what is the probability that a selected person is a Democrat? Am I coming through the, No. Do I have dead battery? No, just, this thing just acts funny on me sometimes. Still yes, no? It is. I don't know, okay. It says I've got good battery, but. All right, what is the probability that a selected person is a Democrat if, and it's if we know the person selected is liberal. Okay? So we're limiting ourselves to people who have identified themselves as having a liberal ideology. And we want to know, what is the probability that the selected person then is a Democrat? Okay? So this is different from this question over here. And so the answer to this would be 306 divided by 689. Okay, because we're limiting ourselves to just, I'm sorry, not 689. I'm doing this wrong. To 5 divided by 530. I apologize. Okay? Because we're limiting ourselves just to those who have self-identified as liberal. Okay? And there are 530 people who have identified as liberal. Okay? So this is number of people who are liberal. And on top we have number of people who are Democrat and liberal. Okay? You have to be both a Democrat and liberal to qualify. Does that make sense? So we have 306 divided by 530. Okay. What is, if I say, what is the probability that someone is liberal given Democrat? This is asking what? What is the probability that a selected person is what? Liberal if we know he or she is a Democrat. So what is the fraction I would use here? So do 306 divided by 689. Can we see that? So on top, it's number of people who are both liberal and Democrat divided by number of people who are Democrat. Do we see that? Okay. And so the generic formula is that the probability of A given B is equal to the probability of A and B divided by the probability of B. And I know that these are not exactly probabilities, they are counts, but because they all have a common denominator of 1858, it simplifies, okay? Technically on top it would be 306 divided by 1858 divided by 530 over 1858, but it simplifies to that. So let's just try a couple more practice problems like this. Is that okay? Did I go too quickly to the next slide?
Just for 2 seconds.
Just for 2 seconds? All right, sure. Okay, now we good? No. Now, okay. All right, so I'm going to just put a few questions here. and put fractions up for these things. So I'll give you guys a couple minutes. You can just write the fractions. I'm not worried about you turning them into decimals. If you want to turn them into decimals, you can, but just come up with the fractions. Okay. Oh, and I'll just put this at the bottom as a guideline. Probability of A given B is equal to the probability of A and B divided by the probability of B. Okay? So I'm just write the fractions. That'll make it go much faster. Okay.
For the other and Democrat, they're both.
Uh-huh.
Gotcha.
No. The dash represents given. Okay? So, did everyone write these problems down into their note sheet at least? And you guys are figuring them out? Or are you guys just staring blankly at? So this is what we did in the last slide. Okay? So you can review that. The vertical bar represents the given. Remember that? And this is what we're working on. Do we need help or are we doing okay? Yes, question. Mm-hmm. So the top part is probability of A and B divided by the probability of B. So keep that in mind. Okay? Do your best. That's all I want you. These are very good questions that you're asking. Okay? And I want you to think what that means. And then even if you can't figure out the answer, when I give you the answer, then it'll make sense because you thought about it. Yes?
Isn't the other and Democrat, are they usually exclusive?
Uh-huh. So you guys are all asking me essentially different versions of the same question. These are good questions. I'm not going to answer them right now. I want you to think about how to answer this, and then we'll go over the answer. Well, at least did you guys come up with fractions for these three? Yeah? We're all good? Almost? Come on now. All right, now I'm going to go over this. Moderate given other, what is the fraction we do? Let's use our red pen. 322 divided by 700. Okay? Questions? Question? Okay. So on the top, A and B, right? So that's going to be moderate probability of, so let me just, okay, so I'm just looking at this, and if we're going to call this A and we're going to call this B, on the top I'm going to have probability of moderates and other divided by probability of other, right? Okay, so what's probability of other? So technically, if I do moderate and other, it's going to be 322 divided by 1858. Is that okay? Divided by, on the bottom, other would be 700 divided by 1858. Do you see that? Yeah? Okay. But then the 1858s cancel each other. So I get 322 over 700. Good? Good. Okay. Republican given moderate. What do I have? 134 divided by 735 or 469? 735. Okay. Over here, what do I have? 134 divided by 469. Okay. So always remember, this is the definition, A given B. So, you know, just label what's A, what's B, okay? And make sure the B goes on the bottom. So B being moderate, what's the probability of being moderate? 735 over 1858. You can cancel those out, so you can just write 735. Same thing with the Republican. What's B? 469. A total of 469 are affiliated with the Republican Party. Is that okay? Okay. All right. So let's do these ones that seem to have given everybody, or not everybody, the questions. All right. Liberal given moderate. This is 0. Okay? Because what's on the bottom? The bottom is technically, if I label these A and B, I have probability of liberal and moderate. Not liberal and B. Liberal and moderate divided by moderate, right? What is the probability that someone is, when they answered the survey, answered that they identify as liberal and moderate? 0. So the numerator is 0. The bottom is technically 735, but that doesn't matter. The top is 0. So the answer is 0. Okay? And what's going on over here? Same thing. We get 0. Is that okay?
No.
No. All right. Who said no? Say it proudly. Okay. What do you have a question about?
I don't understand why it's 0.
Okay. So let's look at so we surveyed 1858, right? Here, let me just go back a couple slides. Do you remember this? Democrat and Republican equals 0? Is that okay? Huh?
Yeah.
And this question makes sense?
Yeah.
Yes. Okay, so essentially it's, I'm asking what's the probability that someone is both a Democrat and a Republican, and the answer is 0, okay? What is the probability that someone is both liberal, has both a liberal and moderate political ideology, according to our survey? Is there anybody that fits in both rows? I'm asking you a question.
I mean, I don't know. I'm still trying to. I don't get this. Any of this. So just explain, and I'm going along.
Oh, okay. Well, I'm trying to explain so you understand, okay? And I don't mean to put you on the spot, but I want to make sure all of my students get it. Okay. So, are you okay with the table and what the table represents?
Yeah.
Okay. And so there are 530 people who answered the survey and said, I have a liberal political ideology. Is that good? And there are 735 people who said, I have a moderate political ideology, and that's okay. All right, and so did anyone say I have both a liberal and moderate political ideology? No. Okay, so there are 0 people who answered liberal and moderate. Is that okay?
Yeah.
All right, so does that make sense? Yeah. So this is different though, okay? This says what's the probability that someone is liberal given that they are moderate, okay? And so it's a little bit different, but the top part, the liberal and moderate, is a 0, okay? So it's kind of like saying, you know, what's the probability? You know, I have someone standing behind this door, okay? And I'm going to tell you, this person, well, people are difficult to deal with. Okay, so, all right, okay, so just because everything's complicated. Okay, but I'm going to say, okay, so this, I will say this we've got a car behind this curtain here, okay? And I'm going to say this car comes from an American manufacturer, okay? And I'm going to ask, what is the probability that the vehicle is a Ford? Okay, so Ford is an American manufacturer, and so the answer is not 0. Maybe it's 30% or 40% or whatever. We don't know. Okay, the car behind the door is an American manufacturer. Could it be a Ford? The answer is yes. Okay, but if I say the car behind the door is an American manufacturer, and I say what's the probability that it's a Toyota? What's the answer there? 0, right? Because Toyota is a Japanese manufacturer. There are Toyota plants in the U.S., but if we say, if you know that it's American, we know that it eliminates the possibility that it's a Toyota, okay? So the same thing here. If we know something someone has identified as moderate, the probability that this person is then liberal is 0, okay? And that's what we've got going on in both of these cases. Does that make sense? Do the other fractions also make sense?
Yeah.
Okay. I will take that and we will go. All right. So let's talk. We're still dealing with this table, and I know you guys love this table. I want to talk about independence, okay? Independence. So okay. When we talk about independence, we're talking about 2 events again, okay? And we say 2 events are independent if the outcome of one event has no influence on the other. All right, so that means, so to check, if 2 events are independent, this must be true, okay? If A and B are independent, then probability of A given B must be equal to the probability of A. All right, and so just think about that. So I'll let you guys write that, and I want to explain, and I want you to think about this. So what this is saying is that if we know B has happened, and we're asking what is the probability that A has happened, if A and B are independent, even if we know B has happened, the probability of A happening is just the probability of A. Okay? So it could be, I could ask, I'm going to flip a coin. And I say, what's the probability that the coin is going to land heads? And you say it's 0.5, right? I'm going to say, well, hang on, let me give you another piece of information. It's going to rain tomorrow. Or and so I say, okay, now that the forecast says it's going to rain tomorrow. What's the probability that this coin is going to land heads when I flip it? And you'd say, still 0.5. And you'd say, flipping the coin has nothing to do with it raining tomorrow. Okay? And that's what we're saying here. Okay? The probability that the coin lands heads, given that it's raining tomorrow or whatever, it's just the probability that the coin lands heads because raining tomorrow and flipping a coin are independent. The outcome of one has no influence on the other. Yes?
Is it possible to have only one independent? Like, it'll affect it this way, but then in reverse it won't affect influence?
No. If it, and it, I guess, don't mistake it for a cause and effect outcome. Okay? So independent means one outcome and the other outcome, they don't influence each other. Okay? Dependent would indicate that they do. And to answer your question, if A and B are dependent, then B and A are also dependent. Okay? You can't have one way and not the other. Okay? So it's not necessarily a cause and effect relationship. Okay? So for example, two events that are dependent would be it rains tomorrow and we see a bunch of umbrellas. Okay? So if it rains tomorrow, what's the probability that you'll see an umbrella? Quite high. Okay? The flip is also true. If you see an umbrella, what's the probability that it was raining? Also quite high. All right? So those two events are related and thus dependent, but it doesn't mean opening umbrellas causes it to rain. Okay? And we know the cause and effect relationship goes one direction in that the rain generally causes people to bring umbrellas, and it's not the other way around. Otherwise, we'd all be opening umbrellas right now and fix our flood problem. I'm not flood. Fix our drought problem in California. The opposite of floods. Okay, so that's not how it works. But the idea of independence just means A given B is that equal to A. So with our data table, I'm going to ask, is being moderate independent of being Republican? Okay? So to check this, if they are independent, okay? If moderate, being moderate, is independent, if they are independent, then this must be true. Probability of A given B equals probability of A must be true. And in our case, that would be the probability that someone is moderate given Republican is equal to the probability that someone is just moderate. Okay? So this is how we check independence. So if I'm asking, is being moderate, is this independent of being Republican, then this statement must be true. Okay? So what is the probability of moderate given Republican? Just tell me the fraction. Okay, just as a fraction, moderate given Republican is 134 divided by 469. Okay? Everyone's okay with that? Okay? What is the probability that someone is moderate in general? 735 divided by 1858. Okay? And so the question is, are these equal? Are these equal? And so some of you are saying yes, no. Okay, well, let's check. So we have to use our calculator here. 134 divided by 469, I get 0.2857. And the other one, 735 divided by 1858, 0.3955. Or 3956. Okay? So these are not equal. So if they are not equal, what does that mean? They are not independent, okay? Is being moderate independent of being Republican? The answer to that is no, okay? Moderate is not independent of being Republican. Okay, and we can see that. So if we know, if I say I've got someone behind this door, and we know nothing about this. I selected one person out of the 1858 people. We know nothing about this person. I ask, what's the probability that this person's moderate? Your answer is almost 40%, 30.3956. Okay, if you know nothing about the person, the probability this person's moderate is 0.3956. Okay, I say, okay, well, let me give you a piece of information. This person is registered as a Republican, so we know that this person is affiliated with the Republican Party. What's the probability that this person is moderate then? Okay, it changes. It's no longer close to 40%. It goes down, and it's now 0.2857. Okay, so knowing that someone is affiliated with the Republican Party changes the probability of being moderate to something lower, and that's 0.2857. So therefore, being moderate and being Republican are not independent. Is that okay? Okay. Now we could have checked the other. If so, in this situation, I arbitrarily labeled moderate A and Republican B, and that's what I did with the equation. I could have switched the labels and called moderate B and Republican A, and I would have come to the same conclusions. My fractions would have been a little bit different, okay, or they would have been different. But my conclusion would have been the same. They would have not been equal, and I would conclude that they are not independent. All right. Okay? All right, so let's try another example. Or actually, we gotta move on here. All right. So study this example, okay? Because there's going to be quiz questions like this, all right? And make sure you can do moderate given Republican. Make sure you can also do, for quiz, no probability moderate given Republican, but also the reverse, probability of Republican given moderate, okay? So study this page and this one, and this one also. Okay, so these examples here, I'd say, are useful for studying. I'll post a practice quiz as well, but if I'm late, just make sure you study those. That should help in preparation. Yes.
So if they didn't share they didn't share the same decimal, it wasn't independent.
Uh-huh.
What if they shared the same?
Yeah. So at this point in our class, we're going to say if the two numbers are not exactly equal, we're going to say not independent, okay? Now in the future, let's say this one was 0.3956 and the other one was 0.40. 0.40 is pretty close to 0.3956. What do we say then, okay? That's a tougher question to answer. So right now we're just going to say they're not the same, so they're not independent, okay? But later on in the course, we're going to do what we call inference. And we're going to say, is 0.3956 close enough to 0.40, or is it actually different? And that's a tough question, okay? It's a little bit harder. But we're going to worry about that when we get there. Okay. So that's conditional probabilities, okay? All right, question, quick question. If two events are independent, are they mutually exclusive? Don't shout it out. And your answers could be yes, no, not enough info. So if we know two events are independent, could they be mutually exclusive? Are they mutually exclusive? Okay, what's your answer?
Yes.
The answer is no. Okay. So what does it mean to be independent?
You don't affect the other.
One outcome has no influence on the other, right? What does it mean to be mutually exclusive?
But if one event happens, then
So outcome of one, so independent means outcome of one has no influence on the other. Okay, mutually exclusive means if one happens, the other is what?
cannot happen.
The other cannot happen. So this is the exact opposite of having no influence, right? Yes.
What about coin toss outcomes?
Okay.
Isn't each coin toss outcome independent of each previous choice?
Yeah. Okay. So this is a very good question. All right. So what about coin tosses? All right. Okay. So for one flip, heads and tails are mutually exclusive. That is true. If the coin lands heads, it cannot at the same time have landed tails. So if I told you the coin, what is the probability of the coin landed heads if we know it landed tails, you would say 0. Okay, if we know it landed tails, this is a stupid question to ask. We know that it could not have landed heads. Okay, for one flip, heads and tails are mutually exclusive. Okay, but for multiple flips, okay, each toss is independent of the others. Okay, if I tell you the first coin flip landed tails, and I say what's the probability that the second coin flip lands heads, the answer is 0.5. The next coin flip is not influenced by the first coin flip. But if I tell you that the second coin flip landed tails, and I ask you what's the probability that the second coin flip landed heads, that would be 0, because for the second coin flip, the outcome heads and tails are mutually exclusive. Okay? So these are actually all different events, okay? Probability of landing heads and tails are different events for the first coin flip, and then for multiple flips, each outcome are different events from the previous outcomes or possibilities as well. Okay? But mutually exclusive means if one happens, it basically makes the other one impossible. That's the opposite of having no influence. That's having influence. Okay? Even if it's not a cause and effect relationship, that means there's some kind of link between the two. Okay? So independent events are not mutually exclusive, and the opposite. Mutually exclusive events are not independent. Does that make sense? Okay, let's talk about probabilities for sequences of events. Okay. So for all events, probability of A and B is equal to the probability of A times the probability of B given A. All right. So A and B, you can think of this as a sequence of events going first A, then B. This can be written as A and B. Okay, first A, then B is essentially A and B happening. Okay, for all events. Okay, if A and B are independent, the probability of B given A, I know I wrote this the other way, but what would the probability of B given A be if A and B are independent? This would be the probability of B, because A has no influence on B. So that means the probability of A and B is equal to the probability of A times the probability of B. Okay. You're going to have a few exercises going over this, and I think that's fine. I'm going to focus more on this one for the independent events. Okay, so for example, like sequences of coin flips or things like that. Okay, so we can think of sequences of coin flips are independent events. All right. Okay, so I could say, I will flip a coin 3 times. All right, let's just start off with 2. I will flip a coin 2 times. What is the probability? The first flip is heads, and the second flip is heads. So we're asking probability of heads followed by heads. Okay, these are independent events. So I would write that this is equal to the probability of heads on the first times the probability of getting heads on the second. Okay, what's the probability that I get heads on the first flip? 0.5. What's the probability I get heads on the second flip? 0.5. So the overall probability is 0.25. Good? All right, so let's complicate things. Okay? Oh, go back? Yeah. All right. It always hurts. When I use the chalkboard, my shoulder would always hurt. And
My hand hurts.
your hand hurts? Yeah. This is the story of my life. I do this multiple times a week. But I don't know. Call me old-fashioned. I prefer writing things out every time than flipping through slides. And I don't know. Okay. We'll keep going. All right, so sometimes you'll have a sequence of events like A, then B, then C, then D, okay? And in that case, the probability of A, then B, then C, then D would be equal to the probability of A times the probability of B times the probability of C times the probability of D. So if all events are independent. Okay, you can just multiply them all together. All right, so let's try something out. Okay, here is, there's an imaginary, there's a bag here, okay? And inside the bag we put in a few stones, all right? There's some pebbles in here. Okay, but one of these stones is, I don't know. There's a white rock in there. So 1, 2, 3, 4, 5, 6, 7. Okay. Or maybe we'll put in two white rocks. Okay, so there's 7 stones.
8.
Or 8. Thank you. Okay, 8 stones. 2 are white. And 6 are black. Okay, and imagine we're in, I don't know, Sherwood Forest, and you're gonna reach in there. Okay, you reach in, you grab a stone. Okay, look at it, and then put it back. So every time you reach in, there's always going to be 8 stones in the bag. Okay, so every time you go in, the chance of drawing a white or black stone is independent of the other ones. Okay, so we're going to play a game. Okay, you reach in 2 times and you win if both stones you draw are the same color. Both stones you pull are the same color. Does that make sense? So you reach in, and you get the same colored stone twice. Doesn't have to be the same one. But if you, as long as you get the same color twice, you win. All right. So what is the probability we win? Okay. So all right. So to win, what are the only ways we can win? So I can win if I get white, then white, or I win if the first stone I draw is black and the second stone I draw is black. Is that okay? These are the only ways I can win. If anything else happens, I lose. So what is the probability of getting white, then white? So I'm just going to abbreviate this: probability white, then white. This would be, so the first one is probability that the first one, white on the first draw, times probability of getting what? White on the second draw. I know you guys are just copying what I'm writing down, but I want to make sure I'm making sense also. Okay, so what is the probability I get white on the first draw? 2 out of 8. What's the probability I get white on the second draw? 2 out of 8. So this would give me, okay, 1 over 16.0625. Okay. All right, so go ahead and find this probability of black followed by black. See if you can figure that out. Maybe I'm doing this too quickly. Okay, so I'm getting 0.5625. Is that all right with you guys? Okay. All right, so what's the total probability of winning? So probability of winning is I can get white then white, or, so I add these, probability of black then black. So I do 0.0625 plus 0.5625, and I get 0.625. So that's the total probability of winning. What is the probability of losing? Yeah, so probability of losing would equal 1 minus 0.625, 0.375. Oops. Yes.
Remind me how you got it for the second problem, how you got 9 on top.
All right. Well, 36. I'm just simplifying. So so just multiplying fractions, right? 6/8 times 6/8 gives me 36 over 64, and if I divide both by 4, I get 9 over 16.
Okay.
So just multiplying fractions. That's all. Good? Okay, so let's try this. Let's go back. Huh? Sure. You can just do the keep this. I'm gonna change it. Can I go to the next slide? Too late. All right, so we'll play another game. I don't know why. This is just a. All right, we're gonna spin a wheel, can draw a circle. It's really hard drawing a circle. All right. On this thing. So we'll say, you know, it's like Wheel of Fortune. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? I can't count. All right, I'm gonna number these. Okay, so you're spinning this wheel, and we will say you win if you get in any of the red spots. All right. Win if you land on red. Okay. Assume all this pie is not drawn very well. Okay, but each spot should be the same size. Okay. Each spot is the same size.
And that's supposed to be 11?
There's 11, okay, 11 spots. All have the same probability, okay? Three are red. 3 spots out of 11 are red. Okay, so you're gonna spin this wheel. That's how we play our game of chance. And you win the grand prize. If you spin four times and get red all 4 times. Okay, so what is the probability of getting the grand prize? Are we trying this? Is this what we got? So, each spot is the same size, 11 spots, all have the same probability. 3 spots out of 11 are red. You win the grand prize, huh? Yeah, you I don't know. You. Okay, is this what we got? Do I need to go over this? Probably. All right. So to win the grand prize, we have to get red on all four, right? So the sequence has to go red, then red, then red, then red. Okay? So what is the probability of this happening? Okay, what's the probability that we get red on the first one? 3 out of 11. On the second? 3 out of 11. Third? And the fourth? Okay, and when we do all of this, we get 0.00553. Okay, so I'll demonstrate. You do 3 divided by 11, and you raise it to the 4th power. And I get that, huh? Here, I'll change this into scientific notation, or not normal notation. 0.00553. Just on my calculator, I changed it. Okay, so I did 3 divided by 11, and I raised that to the 4th power. Okay, everyone's okay with powers, right? 3 over 11 to the 4th, same thing. Okay, let's try another question. You play 4 times. What is the probability you get red 0 times? So what do I do for this one? So it would be 8 over 11 raised to the 4th, yeah? And I get 0.2798. Is that okay? All right, we'll do another one, okay? You play 4 times. What is the probability you get red at least 1 time? So you're playing it 4 times. What's the probability you get red at least 1 out of the 4 times you play? So what does it mean to get at least 1?
3 of them are 8 over 11 and 1 is 3 over 11.
So I'm playing 4 times. So that means how many times do I want red? 1 time. At least 1 means so 1, 2, 3, or 4 reds. That's what I want, right? What do I not want? Yeah, we don't want 0 reds. Okay, so at least 1 red, at least 1 is the complement of getting 0. Can you guys see that? Or can you think that? At least 1 is the complement of getting 0. Okay? If you attempt something 4 times, there are only 2 possibilities in the whole world. It either didn't happen in any of the 4 times, or it happened at least one time. That's it. If you try something 4 times, it either happened at least 1 time, or it didn't happen at all. There's no other possibilities there. Okay? So the probability of getting at least 1 is the complement of getting 0. So what can I do? I can do 1 minus the probability of 0 reds. And so that would be 1 minus what? 0.2798. So the probability that I get at least 1 red is 1 minus this, and that's 0.2798. 7202. You remember? Does this make sense? Yes?
Yes.
Okay, I like that yes. Okay. Well, I guess we'll stop here. And what does what? Okay. I mean, we're finishing a little early. Okay. I hope no one's too heartbroken about that. So we'll stop there. Study.